Let us take a look at our fourth example, and then we'll go through various steps during this example. In the first step, we have a charge Q which is released on the inside sphere. So we have two conducting spherical shells. Let's call this radius A, and this is radius B. And we release a charge Q on the inner conducting shell, and we release charge minus Q on the outside conducting shell. Where and how will this charge be distributed on the various shells? Well, as we have seen, when we release charge on a conductor, it tries to go to the outermost surface. So this charge which we have released, and assuming again it is positive, this charge will go and will sit on the outside surface here. And since that surface is very symmetrical, the charge would sit uniformly on the outside surface. So I would get a uniform charge with some density which would be given by the charge divided by the surface area. And it would sit on the outside surface of the inner conducting shell. Where would this minus Q charge go? To think of it, this minus Q charge would be attracted to this plus Q charge. It wants to go and meet this plus Q charge, but it can only go to the surfaces. So this minus Q charge will come and sit on the inner surface of the outer conductor. And again, because everything is symmetrical, so this charge would again be uniform and would have a charge density minus Q by 4 pi V square. I'm just drawing it right here, but I mean that this is actually sitting right on that surface of the conductor. What would the charge outside be? That would be 0. There is no charge on the outside surface of the conductor. All this charge would be attracted towards this plus Q. So that is how the charge would be distributed on the shells. In the next step, now we are saying that we take this and we have grounded the outer shell. What would happen? Again, remember, we have charge sitting on the outside surface plus Q. This charge has nowhere to go. That charge can't really go anywhere. There's no path for it to go any further. And we had said there was charge sitting minus Q, which was on the inner surface over here. This particular charge is attracted to the charge plus Q. That attraction hasn't gone anywhere, so why would this charge want to leave the ground? This charge would still stay there. So nothing will change. Everything will remain the same. Nothing would change in the problem. You can also see it from the potential point of view. Before we did the ground, what is the electric field outside? Well, you can easily make a Gaussian surface. Everything is symmetrically distributed. So we make a Gaussian sphere, then we get E 4 pi r square is the net charge by epsilon naught, and the net charge is 0, so E would simply be 0. Electric field outside anywhere here is 0 in the beginning problem. So if I was going to calculate what was the potential at that place, R is equal to B, what I have to do is integrate the electric field from B. Electric field outside is 0, so the potential at that place is 0 already. And thus, when I grounded this plane, nothing changed. The potential there was already 0 and connected to another 0 potential. The answer does not change at all when I ground the outer conducting shell. In the last step now, instead of grounding the outer conducting shell, we are now grounding this shell over here. If we were to ground that shell, would the answer change or not change? And again, remember, there is a negative charge sitting here. We have given that charge to this conductor. So there is a total of minus Q sitting on the outside conductor. That minus Q can only distribute itself in the conductor. It can go and sit on the inner side, or it can go and sit on the outer side, but it has nowhere else to go. When I ground the inner conductor, it has still no path to go anywhere. So that conductor and this conductor still will have minus Q charge. However, the charge which was sitting on the inner conductor has a path to go to ground, and how much of it would go to ground? What does the ground want to do? The ground wants to make sure that the potential here is 0. That's what the ground is doing. It is making the electric potential on that inner conductor to be 0. So the charge in the inner conductor, charge at R is equal to A, will change till it makes the potential at that point to be 0. How can we calculate? So now basically what we have to do is calculate the potential at R is equal to A. Since charges are distributed on spherical surfaces, again using what we learned in example 2, we should not really calculate the potential at A, we should calculate the potential at origin right here. Why? Because whatever charge is present, that charge is going to be equidistant, same distance away from the origin, and my calculation is pretty straightforward. I don't need to calculate electric fields. I can simply say that the potential there is K multiplied by the total charge divided by the distance. Let's assume that there is charge QA present on the inner sphere. So the potential at R is equal to 0 is going to be the charge which is present at A, potential due to the charge which is present at A, total charge because it is same distance away from the origin, plus the potential which is due to the charge present at B. And because we have grounded this sum of potentials should be 0, and thus my QA should be A by B Q. And since A is less than B, it is telling me that this term is less than Q. Some of the charge which I had put on the inner surface, on the inner conductor, went to the ground. The other charge remained, and it adjusted itself such that the potential on the inner conductor became zero. So how would the charge be distributed? We would have a charge of QA given by this expression, uniformly distributed on the outside surface, and then this charge QA is going to only attract minus QA on the inner surface. Of this total charge, a minus Q which was present on the outer conductor, only minus QA is going to be attracted to this plus QA. They just want to mean that once everybody has a pair, nobody else would like to come in there. So minus QA charge is attracted towards this plus QA and will go and sit on the inner surface, leaving a charge of minus Q plus QA on the outer surface. That's how the charge would be created, would be distributed once we ground the inner conductor.